Okay, so I'll talk about a little bit, analytic and theoretical things. So far, we look at the just really, algorithms and then the methodology for, system identifications, both the non-parametric and the parametric, right? So just a quick reflections. The simplest case, so we like to identify the some transfer function like this, and the parameters A's and B's are things that we like to estimate. We use the prediction error model, and then we use the identification input-output data, and then we minimize the prediction error between the actual measurement YT and then predicted from here, right? So now this is very broad. It's not it's a basic formulation that can be applied to a much broader class of systems, and not just this is a it's a simple single input, single output transfer functions. But a basic concept should be applied to a broader class of systems. Now, two theoretical questions, both are very important. You care. What is the so-called consistent estimate? And in the statistics areas, it's being called the unbiased estimate. Now, what we like to do is basically we collect the data, totally n the data points are created then from experiments or simulations. And the question is that as you extend n to infinity, are you guaranteed to reach the true value? Of course, so for finite number of n, depending on the samples, you get a little bit different estimate for theta n. But as you get more and more data, are you guaranteed to reach the true parameter values? Is your effort and push to infinity worth doing? Otherwise, no need to work too hard, right? So this is very important. Now, this is, as I said, basically the same property, so-called unbiased estimate, under ergodicity assumption. So this is the ensemble mean, and then this one is time average, or the number of samples. That's actually equivalent to say time average. Basically this is very fundamental important properties in that. Now this requires quite a few conditions to satisfy. Perhaps 3 or 4 most important one is that you have to pick the right model for the systems. If the model is significantly different from the real system, no chance, right? And second point, of correct prediction. What I mean by this is that just we discussed last time some naive way of predicting this actually output y hat. Turns out to be a wrong prediction. In particular, when the systems is subjected to colored noise comes in, then if you just so simply neglect those noise components, you got the wrong, basically not the best prediction. So the error here may be due to both actually the parameter values you picked is wrong, so that you can actually correct this based on this one, but also the prediction is not actually right to formula. So somehow this one is to request the change to that actually prediction formula too. So our goal is that pick the right model. And then we like to actually estimate the parameters like this. In order to do that, we must be able to put together the best prediction that you can do given the model, and then given the parameter values, we must be able to provide the best prediction. And then the error basically reflects the wrong parameter values you picked in here so that we can correct this properly. So that's actually important stuff. So last time we introduced the one step ahead predictor. That actually plays a very important role to assure the second point. And also naturally, by doing so naturally, we model the noise dynamics. Remember that? And the way we model the noise dynamics is that noise is originated by white noise random signals, truly unpredictable random signals, and it goes through some dynamic process, thereby it gets colored. So that actually process from white noise to colored noise, that's actually some transfer functions is involved, and what we like to do is to estimate that transfer function, the parameters associated with that the noise dynamics transfer function too. So that was actually one of the important results we got the last time. And also persistent exciting the data is needed because if UT is not exciting the system enough, you have no chance to get this consistent estimate. Now, the second question, which is a little bit more practical side of the question, is basic convergence speed. So, even though you are guaranteed to reach this in true value, as n tends to infinity, no one really can do, no one has the infinite resource to do that. So n must be finite, right? So how finite is finite? How large is large? Is a very important issue from a very practical viewpoint. So how many data points are required, right? And also, important is that what are major factors influencing the convergence speed? That's actually interestingly depending on your choice of a model, and if you parameterize the model in an appropriate way, surely you get a very slow convergence. So how do we really know that? And then this second point is actually today's major topic, and then you get some theoretical background to address this. And this is actually the issues, increasingly important as things are going towards more data-driven systems, right? We now use the data every day, and it's so important to use the data very effectively. And actually, the boil down to these two questions: do we have enough data? Are we actually picking the right stuff to go to the true values? That's actually the basic questions. Okay, so what we like to do is this: analysis of asymptotic distributions of estimated parameter values. Okay, here are the things. Initially, you collected some small number of data, maybe 10 data points, and then actually you repeat that experiment many times. So every time you get the 10 data, you plot the result. Then your results, basically estimated the parameter values, may have some distribution, right? If the data points are small, distribution is kind of a wide spread like this. And you work hard and then collect the 100 data, you get the a little bit actually sharper concentrations, and then you work very, very hard, and maybe you hired another 1 or 2 Europe students and get more data. Then it's very sharp like this. How quickly this one converges to this? And at the end of the day, where we are converging? And if I just summarize today's, summarize the major results of today's analysis, it's going to be, these 4 points. It's convergent rate. This one converges to this at the rate of, proportional to 1 over square root of n, 1 over square root of n. And error distribution, this error distribution, initially it's not actually, a perfect shape, but at the end of the day, it is going to a Gaussian distribution. No matter what the distribution originally had, it's going to a Gaussian distribution. And the covariance the matrix, so we can actually compute associated with the this Gaussian distribution. And then this covariance, basically, the error from the mean value. It depends on noise intensity. If that's a very noisy process, it is to deteriorate the performance, right? And then also second point is very, informative and very important. That's the sensitivity of predictor y hat to parameter values. So, if this guy is parameterized in some way, and this prediction based on the model structure and then the parameter, theta, we construct y hat, right? If you take the partial derivative with each of this parameter, theta, and then you can just look at that. And if this one is very small, sensitivity is small, you have a difficulty to identify that. And the convergence is very slow. Okay, so you should not pick the structure, or you should not pick that kind of parameters, which is to cause a very slow convergence. Okay, now one big bonus is that after you know that the distribution is Gaussian, and you know the covariance, then what you can do is to apply some statistic treatment, like a confidence interval. So here's the normal distribution, right? So you can say, as you collect the data, such and such, number capital N of, the data, you want to be guaranteed that the, your experimental, system identification results is basically, 95% within such and such, error range. So, accuracies and, 2 sigma accuracy can be achieved with, 95% of the chances. If you repeat the experiment 100 times, 95 times you get the result, which is actually within the 2 sigma plus minus 2 sigma range. That's sort of a quality control of your system identification experiments, and it can be obtained. Okay, so it's very cool, right? So this is something we like to use when you design the system ID. Okay, now theory. What we like to do is to use the central limit theorem to this problem. That's a very natural choice, right? So we aim to analyze the distribution of estimated parameters, okay, by applying the central limit theorem. I think central limit theorem, at least you have heard of it, right? So here's the population distributions. Okay, distribution is arbitrary. It's not necessarily unimodal, multimodal, any ugly distribution. You pick n samples from here. Okay, so x1, x2, and xn. Okay, and first you compute the mean of this sample. Okay, 1 over n. Compute the sample mean of this, so mu is actually, mean value. So now if you basically, compute this and then compute the, mean of the samples of these particular samples. Okay, well, of course, we don't know mu initially, but let me see, just, we don't have to worry about this, say that this guy, then actually, I just want to, plot this Gaussian with 0 mean, but it does not actually, this can be suited to any point. So let's forget about the mu. Okay, so if you basically compute the sample mean, okay, sample means also random variables, because depending on this in the sample, sometimes you hit the higher value or smaller value, right? So it has some distribution, but that's actually distribution as n tends to infinity, it converges to a perfect Gaussian distribution. That's the central limit theorem. Point is that no matter what distribution you originally have, but as you have enough number of samples, the mean of that samples going to be Gaussian distribution. So CLT tells us the mean of samples of size n drawn from a population with an arbitrary distribution tends towards a normal distribution as the sample size tends to infinity. So, let's see a random variable xt, multivariate random variables with mean value m. And mean value m, this process itself is basically, stationary. So, you have m for all n, all t, excuse me. So, then, if you think about the covariance, xt minus m, you compute this guy for all t, and actually consider the sum of xt minus m. And in fact, xt minus m, t equal 1 to n divided by n. This one is mean, right? Now we multiply square root of n to this. In other words, sum of xt minus m divided by 1 over square root of n, and then we define this variable to be this random variable to be yn. Yn is the square root of n times the sample mean. Okay, so if this is the case, as n tends to infinity, the distribution of yn converges to a single Gaussian distribution. This one, tends to, as n extends to n, this tends to normal distribution with zero mean, and actually covariance Cx as defined here. So we will apply this theorem to find the distribution of a parameter, estimate theta n hat for a large n. Okay, so that's the point. Now, we started with a very simple model that's ARX autoregressive with the exogenous input. And that's the system that we looked at that the last time. And the good thing with this, ARX is that the noise comes in, any lines are here. It has to go through some actually autoregressive part, and going out in this way. But this particular noise structure makes it very easier because the prediction is actually what is this? Linear regression. Yeah, the same analysis can be expanded to a pseudo-linear regressions, so that model like a Rmax model can be actually dealt with. But today's lecture, we just assumed this one, but this one can be extended, okay, relaxed. Also, we assume the model structure is correct. So ARX model is like this. And this is the true value of the system, the theta naught. And if you run the experiments, take the experimental data, input the output data. Output is basically produced, through this through model, the same result obtained. Okay, again, the theta naught is the true parameter values, and this actually, white noise has this properties. Lambda is the variance, and that happens only t equals s, and otherwise 0. It's white. Okay, totally uncorrelated. So and then next one is just as usual, we assume the ergodicity. So an ensemble mean equals the time average. Okay, and then input the UT is persistently excited. Most of the cases, UT, we use some random signals, which is not correlated to VT. That's actually, things we've been using, to improve the performance. Okay, now asymptotic distribution analysis. So under the above assumptions, input-output data are collected, and we apply the least square estimate for determining the parameters, right? And the question, where is the distribution of the parameter estimate converging? And what happens as we collect more and more data, okay? So I know we apply the central limit theorem. We need to go through 3 steps. This analysis is a little long, so please bear with me. Step 1, if theta n hat is the solution to the least square estimate, basically this is the prediction error metric, right? Quadratic forms. And if this guy is a solution, to our least square and estimate problem for data n is now finite. Okay, n is finite. Okay, so for that data, this is the best one. So derivatives with respect to theta, and it's evaluated at the theta n hat is 0, right? In other words, if you plot the Vn, you see Vn against the theta, you have some kind of a curve like this, and this is a convex optimization. So you have a single minimum point over here. That's actually the best one for this set of data, capital N, data points in it. So theta n hat, this slope is 0. Okay. And also, I have to note that so for finite n, if you evaluate this at the true value, theta naught and theta n hat is basically different, right? Different. Even though theta 0 is actually a true case when n extends to infinity, but for finite one, this may not be 0. May not be 0. So it's a little actually confusing, but theta naught is the best one, the true one. But that is the case when you have the infinitely large number of samples. Okay, but if you pick the finite number, and that's a particular sample, even though you plug in the theta naught, this may not be 0. And it is 0 at this theta n hat. So let's plot this one like this, theta naught and theta n hat, and staying like this. Okay. Now we apply the just a very simple math. It's called the mean value theorem. So when you have a continuous and a differentiable function fx within the interval ab, there exists at least one point x equals c between a and b, where this actually formula is held. What this means graphically is that, say, I plot the x versus the fx, and then the particular value a, it takes an fa, and a particular value b, fb. Now the function goes, like this, Okay, so first, let's actually obtain the slope of this one. So slope is given by fb minus fa, this y, difference, divided by x-axis difference, b minus a. This one is to give the slope, right? So mean value theorem tells us that there exists at least one point c, and if you take the derivatives of this function fx, and then evaluate at the c, that's f prime c, this slope is basically the same one as this slope. So, as you, change the slope and here, a slope varies continually. At a certain point, it actually agrees with this slope. And then that is actually mentioned here. So, the slope is same one, F prime C, and the C exists between A and B. Or we can write it FB minus FA equal F prime C times B minus A, right? Now, what we'd like to do is to apply this one, apply this mean value theorem to this function dVn d theta. It's not actually Vn theta, but we apply to the derivatives of quadratic function, prediction error function Vn. So originally we had this Vn and then take the derivatives, we got this kind of plot, and this is to show the derivatives. So at this point, the derivative is 0. So it is actually crossing 0 at this point, right? And then actually move up to this slope is some value, and which is indicated here. Okay, this is theta naught and the theta and hat. Okay, and then this is differentiable continuous function. So we can apply the mean value theorem. So, we see this slope can be actually created, is actually equivalent to at least one point of, say, C between this value and this value, and take the derivatives. So this slope is the same as this slope, right? So FB is now this guy. So Vn b d theta evaluated at the theta naught. B naught is this, right? Theta naught minus Fa is basically derivatives of this guy in here, and evaluated at the theta and hat. And it turns out that this guy is 0, right? And if F prime is the derivatives of this function, So the second derivatives evaluated at C in here. And then actually B corresponds to theta naught and A corresponding to theta and hat. So this is interesting, useful result, right? I know we can solve this one for the discrepancy between, current estimate theta and hat versus the true value theta naught. So let's solve this one, this equation for theta n hat minus theta naught. I just changed the sign over here. And so this guy is basically, theta is n-dimensional vector. So this is to provide n by n, m by m matrix. Let's assume this one is invertible, which is the case as we discuss later. Invertible. Then we can solve this one for here. So inverse to this n by m matrix times this particular part, d theta and d theta, evaluated at the theta naught. Okay, so we basically use this guy, and then turns out that this one going to, as n tends to infinity, distribution of this one, turns out to be a Gaussian. That's the thing that we like to do. So now let's compute this, d and d theta. Okay, evaluated at the theta naught. Okay, so remember that let me just move you. Okay, so first we like to evaluate this part. Okay, so this is the the main result from the previous page, this guy. And that Vn is quadratic form, so turns out to be this. And then first we apply the derivatives. So it actually 2 comes out, and then theta is involved only this term. So what you need to do is to differentiate, with respect to theta for this term, right? So leaving this one here with the minus sign because the minus sign over here. Okay, so to this, let's use the the predictor. So that's actually linear regressor, right? So for this ARX model, it's a linear regressor. So theta is basically factored out in this way. So let's first substitute this one into here, and then that will result in this guy, right? And also this derivatives with respect to theta is just to pick up phi. So for this part is actually phi. So I just put this one phi over here. And then this other whole need to be evaluated that the theta equals theta naught, true value. Of course, we don't know the true value, but for this kind of mathematical analysis, the theta naught assumed to be existing. So we can actually use this one for analysis. Okay. And later, it turns out we don't need to know theta naught, but in the process of proof, we need to use this because this one is existing. Okay, now remember that the another big assumption we made is that the process model is correct, and the actual measurement that comes from the process model with the true parameter value theta naught, right? So y naught can be yt can be replaced by this. So let's put this one into this, and then this must be evaluated at theta equals theta naught. So we have theta naught transpose phi sitting here, and it also comes from theta naught transpose phi t. These two cancel out, leaving only E naught t, right? So I know this other whole can be simplified in this way, minus 1 over n E naught phi t. Okay, so this particular expression, we call that the B. This one is to be used, for actually, applying that basically, central limit theorem. Remember central limit theorem? We actually consider this yn, which is actually, sum of mean, sum of the, samples t equal 1 to n, deviation from the mean value of the original distribution. Okay. I said something inappropriate. I said that m is not known. No, and that's not true. I know, since whatever the arbitrary distributions, but for that one, we should be able to compute the mean value. So m is known. Okay, so what we like to do is applying the CLT. We use this E naught times phi t. The random variable, xt for this one. Okay, and to apply the CLT, we have to check a few things. A few very mild conditions must be met, right? So one is that the average value of this one, should be actually uniform, and mean that for all the time t, it should be the same. Right, so that's one condition, and also we have to do some covariance analysis too. So let's move on to that. That's step 2. Evaluate the mean and the covariance of random variable E naught phi t. This is the candidate for random variable xt used in the central limit theorem. Okay, let's first check the mean value. This is easy. E naught phi t, right? So taking expectation, how's that? Well, we can check the what's inside of phi t, that's a regressor. So remember that, and the input to t minus 1, t minus 2, blah, blah, blah. And then this auto-regressive part, minus yt minus 1, minus yt minus na are involved. But none of the variables involved in here, correlated with the et, which is the white uncorrelated random signals. So these two are uncorrelated. So this is basically 0. Okay, mean 0. So next we evaluate the covariance, but covariance with the mean 0, that's basically the same one as correlations. So basically, expectation xt st, and then if I write this one, substitute into this expectation phi t, e naught t, and this part transpose phi. E is actually a scalar quantity, phi transpose, and then E0 S, right? From 2 time, basically time slices, T and S. So now let's compute this, for T equal S, CXTT, you can write this one in this way, S is now replaced by T. So obviously, this one actually E naught the square, and this one, the phi transpose. And these two are not actually correlated at all. So this expectation can be taken separately between this part of expectations and this part of expectations, right? So this part is actually this is to show the original noise strength and basically noise variance, and usually we use this notation lambda. Okay, white noise with the strength of lambda. Okay, and then this part, we see this many times, but at this time we represent this, replace this by R bar. Okay, phi transpose expectation R bar. Okay, so we can define the R bar to be like this and the lambda to be this. Okay, so this can be written in this way. Now, T larger than S, evaluating this, let's consider the situation T greater than S. Then what you have is E naught, and the rest of part are not correlated at all, right? Because you see that, from the, the second equation to 2, we have E naught T, E naught and the S, E naught the S, if they are different, they are not correlated, right? The others are basically the same thing in here. No way that the E naught at the time t equal t is correlated with the previous value, all listed here. So no chance that we have some correlation. So they are uncorrelated. So again, we can split this one between the two parts. And this particular part, the E naught the t, is basically a 0. So this one all 0. Okay. Same thing applies if t equal greater than s. So all together, if t and s are different, it's all 0. Okay. So both mean and the covariance of ex, we use E naught phi t as a basically random variables. And then all these results are actually irrelevant to the time t, so it's a uniform over time t. So that's actually satisfy the central limit theorem conditions. Okay, so now we are ready to apply central limit theorem, to this random variable phi t E naught. Okay, so step 3. From step 1, we have obtained this, right? This one comes from mean value theorem, and now let's compute this guy, this one. Oh, we haven't done that. So we need to evaluate this at the theta equal c, some particular value between theta naught and theta n hat, right? So, we already know that this first derivative, which is actually, computed in this way, right? And then we take the one more derivatives. Here's our good assumption. It makes sense because we assume the linear regressions. So, differentiated with respect to theta, only phi t remains. So this becomes the phi t transpose. Okay. Now this must be evaluated at the theta equal c, but a good thing, this is no longer the function of theta. So this, unclear part is basically not an issue. So this is computable. And then we have defined this guy to be odd bar in the previous analysis. Well, to make it a little bit stringent, I would say that the odd bar was originally defined. Let me just push back. Defined this way, which is actually ensemble mean, right? Ensemble mean. Whereas the current case, it is basically kind of time average, isn't it? Right? But because of the ergodicity assumption, these two are the same and tends to infinity, this becomes an R bar. Okay, so that's kind of a neat, pretty neat mathematics, assuming the ergodicity. So finally, we can put together, all three components, A, B, and C, to get the final results. So from A, theta, and so this is the, A, right? So cut and paste in here. And we like to multiply square root of n to both sides. So, first this, square, second derivatives, that's matrix, evaluate to the C, and then we take the inverse to it. And then times this part, we multiply square root of n over here. So, this one, as you can see here from, result to C, this is replaced by R bar. So R bar inverse is sitting here. Okay. And, this particular part is basically, we compute this one. Remember that we compute this. And this one is now 1 over square root of n. Basically, 1 over n, then the square root of n comes in, and it becomes 1 over square root of n, right? This is expanded into this form. That's actually, part B analysis. Part B analysis, remember that. And then now we apply, we treat this mean, sample mean as random variable yn. Yn is basically defined to this. And according to a central limit theorem, this one, as n tends to infinity, this is converges to normal distribution with zero mean. Yeah, the zero mean. And then actually the covariance, Cx. Okay, now we arrive at the almost final results. So, yeah, so the end result is that, we wrote square root of n theta n hat minus theta naught is given by R inverse times that actually, new variables, random variables yn. I'm just talking about this, right? This is replaced by yn, right? This is replaced by yn. And yn follows this rule, right? Converge to that. So I just wrote that way. So R inverse and yn. And this yn converges to normal distribution with the covariance R bar lambda. Okay. So yeah, remember from B, prime, let me just push back to that. Then we did it here. See, we compute this guy, right? And the T equals S, blah, 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 end up with the R bar times lambda. Lambda came from here. Remember that? So yeah, that's actually here, sitting here, R bar, lambda. Okay. The covariance of yn is, R, lambda. But what we want to know is the covariance of this guy, R inverse yn. So there's a little bit of mismatch. Central limit theorem tells us, yn converges to this, normal distribution. But what we like to do is to, examine the statistical behavior of this guy. Theta and hat is actually away from theta naught. How this one converging, to the true value. That's our interest, right? So, and then, difference between yn and theta n minus, theta naught is basically, needing this linear transformation, R inverse. So we need to find the covariance of this guy, okay, rather than this one. So how we really do that? Let's recall the following. We have done this a long time ago, but I know. Suppose that y equal ax. Okay, so this is actually view. Okay, the yx and not related to the previous one. Just actually think about y equal ax. And the covariance has been defined for x, cx equal expectation xx transpose. Okay, that's actually a mean 0 in the case. Okay, then what we like to do is the covariance of y, and covariance y. We substitute this equations. A is pushed out, and sandwiching this part from both sides. So the result is A cx A transpose. Okay, so let's use this transformation formula to our problem, where what we need to do is basically for the place of x, we consider yn. So covariance is originally defined for actually x. That's actually defined for yn. Yn's covariance is this guy. So r bar lambda. That's actually original covariance. And then now what we like to find is this guy, and then so this part is basically y, our actually objective, right? And relationship to x is basically r inverse. So matrix A converting from x to y is basically r inverse. Okay, and our goal is to find the distribution of y, which is our goal is to obtain this distribution that is given to this guy, this distribution. So y corresponds to this. So just going through this replacement, covariance of this guy is QR inverse. That's basically matrix A, and the CX is basically R lambda, and then A transpose R inverse the same, because R is actually symmetric matrix. And these two R inverse R cancel out. The result is lambda times R inverse. This is the final result. So we're not saying the yn converging to this. Now we can say this one converging to this guy. So square root of n times theta n minus theta naught. This distribution converging to normal distribution with 0 mean, and this covariance lambda times R inverse. Okay, the error this guy decreases at the rate of 1 over square root of n, right? So the end part is something like this. Maybe this figure may be useful. So yeah, here we have finally it converges to this distribution, right? And covariance is given by this. And this is the case when you plot this, okay? Plot the square root of n, theta n minus theta naught, okay? Always converging to this single normal distribution with this covariance, okay? Now, this is all confusing. So instead, if you plot this against theta naught hat minus theta, true value. So this is the deviations of your least square estimate for the finite samples. Theta n hat deviation from theta naught is actually distributed in this way, and then depending on the value of n, plot is different, right? Because you need to, it was originally square root of n. Now it is, you remove that, you have to make adjustment on this side. So that's a large n, you get the very, steep distribution like this, and the smaller n, you have a, kind of gentle distribution like this, randomness is higher for small n. So we can say that this one converges at the rate of 1 over square root of n, I would say the standard deviation in this case, converging, at this rate, 1 over square root of n. Okay, so just one, quick question. So, what we found is that then if you, plot the square root of n, theta naught minus theta naught, this is converging to this with this, covariance, right? So, as I plot originally, here's actually the way that is converging, right? So just a quick question, okay? So I think many of you supervise or serving as a mentor of Europe students, right? I don't know what the sort of system Harvard University has, but I know that suppose some undergraduate students working for you, okay, and assisting you taking data and so forth. The students actually came back to you with some handful data, n equal 10. Okay, and then if you actually identify a system, then the result had some significant standard deviation. Okay, you want to actually reduce the this error to 1/10 of the current error level. How many data does your Europe have to take? More. That's a question. How do you think? How do you think? Not just that.
Is it 1,000 total?
Yeah, right. Not 100. So starting with the 10, right? You want to reduce the standard deviation to 1/10 of that. We just thought about maybe 10 times more data, and 100 data points would be good enough. No. If you to reduce that the 1/10, you have to take the 100 times bigger number of data, right? You need to ask your boss to hire more Europe students. So that's the consequence. Okay. So yeah, that's actually obvious things from this diagram. But as we deal with the more complex cases, that's not necessarily true. So, kind of discussions about the result. The covariance depends on, first of all, this one, the lambda comes out, and it's obvious, noise strength comes in, right? Even the R inverse, depending on the model structure, lambda may comes in. Okay, so, yeah, input, so R, if you look at the R's actually definitions is basically ensemble mean of phi transpose. The inside of phi is basically a y and the u's, right? So, obviously, if R is large, then actually R inverse is small, that the covariance is small, that's good, right? So how you can make the R is big? Okay, you have an input to UT and then observation YTs. These must be big. These must be big. So, larger regressor, you can get the better, covariance. So maybe the process converges more quickly. Okay. The other thing is that, in this simple case, the predictor is given by this linear regressor, right? Where, linear regression, where parameter theta is basically separated out from here. If this is the case where, it's not the linear regressor, but pseudo linear regressor, phi depends on the theta too. So, remember that the where phi comes in, it's basically, derivatives of y hat with respect to theta. Okay. If this actually, the, derivatives is large, meaning that y hat highly depends on theta. In other words, sensitivity of your predictor, y hat, to your parameter theta. If that sensitivity is high, phi becomes large, then R becomes large, then Q covariance becomes smaller, right? So that's very good things. On the other hand, if you include some parameter theta, which is not really actually influencing your prediction of y hat very much, meaning that this sensitivity is low, small, then phi is small, R is small, R inverse is large, so Q is big. So that's bad. So the higher the sensitivity, the faster the convergence. If an unnecessary parameter is involved in the model, it may have a low sensitivity in terms of this, which may slow down the convergence. That's the story. So when you select the model, you must be careful. Okay, you can't actually put many parameters. So you must make sure that the parameter theta playing the certain role, having some footprint, some actually right sensitivity is needed in that. So that's the things that we can learn from this analysis. Okay, now shall I? Let me just show one example. This one is strongly related to the PS number 4, which I released yesterday. The last question is on this asymptotic error covariance variance analysis, and I attached some notes. And this is actually the same copy as that note. Okay, again, let's consider the simple ARX model like this, right? ARX model. And, these polynomials are given by, in this way, 1 plus AQ inverse, BQ, this guy, the BQ inverse, very simple case, okay? And, the random, the noise here is basically white, and the strength is lambda. Okay, covariance is lambda, and then let's use the random sequence uncorrelated random white random signals UT is given to the systems, and then that UT is actually uncorrelated with the ET. Okay, and then UT's strength is also denoted and given by mu, like this. So we use actually a random up and down random signals for estimating the systems. So we want to identify the system with the two unknown parameters, theta A and B, right? Based on the prediction error method. The predictor of this ARX model is given by linear regression like this, very simple, right? And with the regressor, in this case, y minus yt minus 1 and ut minus 1. This is the one that we did before. So, here's the things. Before conducting experiments, you want to find the asymptotic variance of parameter estimation, where your parameters to estimate the A and the B converges to the true value, how quickly it is going to converge. Using an estimated asymptotic variance, one can design experiments and how many data points would be needed for estimating parameters to meet the given confidence intervals. You both said that must be 2 sigma 95% of such and such. Okay, so the following analysis, asymptotic variance, is be useful to answer these questions. So, the main part from the analysis is that, as n tends to, as n is sufficiently large, then your estimated parameter values, A and B, having some normal distribution with this covariance, right? So A and B are two variables to be estimated. So variance Q is actually a 2 by 2 matrix, right? So definition to R is given by this, and computing this. So expectation can be taken individually. So this times this becomes 1 element here. This times this becomes 1 2 elements sitting here. So these are all basically autocorrelation and then cross correlation, right? The autocorrelation, this is RY0, and then this one, basically this is the input strength, so mu, variance mu. And here, u to y, time difference is 0. So RUY 0, RUY 0 with negative sign. Okay. Now the challenge is to find the RU 0 and then RUY 0. If we know that we can actually establish this, asymptotic, parameter estimation error covariance, right? That's great. But we need to know RU 0 and RUY 0. How can we really define it? So we basically assume this model, and if this model is true, using this model, we can basically compute these. Okay. Of course, we assume that the input use it's basically white noise with the variance the mu and E as such. So what you can do is the following technique. So this is the model, right? So we first multiply yt minus 1 to both sides. So yt and then yt minus 1, and then we take the expectation, okay? And then this one too, and then this one too, and this one too. And the e and the y are not correlated at all, so this is 0, right? And the others are auto covariance and then cross covariance, right? So auto correlations. So time difference is 1, so RY 1. Okay, time difference 0, so RY 0. This one, U to Y, time difference 0, so B times RUY. Okay, we get to one equation. Now, similarly, we multiply YT to all terms here and do the same, YT square, YT minus 1, you get the, this equations. And then do the same if you multiply ET, UT minus 1 to this equation, you get the other equation like this. Okay, so by solving these 5 linear simultaneous equations and solve this one for RY0 and RUY0, RUY0 is basically a 0 on here, that's simple. But RUY0 is a little bit complicated, but we can compute this, from these equations, this is the results. So putting this one back to the let's push back this way. So we started with this, right? We want to find the parameter estimation error covariance Q, that's a 2x2 matrix, because we like to estimate both parameter A and parameter B. Parameter A and parameter B are involved in this actual model parameters, right? A and B, right? So, we want to compute this, and we just finished the computation of R bar, which is actually here. We now know these parameter values, element values, and put this one into this, to take the inverse and then multiply lambda to compute the Q, and here's the results. Okay, so R inverse, basically this one is to give the diagonal matrix. So yeah, this RY0 basically here RY0, and take the inverse reciprocal to this and then multiply this lambda, we get to this expression. And then, this is a 0, R, UY 0, the 0, so putting here. And this guy is RU, the 0, and that's actually mu, and then taking the inverse and 1 over mu, and then multiply lambda, we get the lambda over mu. Okay, so how do we, interpret this? So this one is basically associated with the estimation of parameter B. Parameter B converges to the correct value, with this error covariance. And lambda is basically a noise variance, and mu is input variance, right? Input magnitude. So this is exactly the reciprocal to signal to noise ratio. Signal is basically input to strength mu, and then the noise is basically lambda. So this is to show the simple signal to noise ratio inverse, right? Now here, the estimation of parameter A, that's actually autoregressive part, is a little bit more involved, right? And then this one is actually converging as for large N. It actually, with this, error covariance, right? So, larger mu is really helpful. But it's a little complicated. Lambda is actually sitting on both sides, so it's not that the simple things. But and also depending on the true values of A and B. Of course, before doing the experiments, we don't know true value of A, B. That's actually with the bar A bar B bar. We don't know, but you can do some actually test. You have some idea as to A should be such and such between such and such value, B should be such and such value. You can actually evaluate this for different possible values of A and B, and then get a sense how much distribution that you have in here. Then you set the goal, how many data points are needed, how many how large N should be to guarantee the result is within the certain confidence interval. So that's the way we can actually do this kind of analysis, and that's the case where we use this theory. Okay, lots of questions. Okay, Charles Dawson, does this generalize to multivariate noise? So, Charles, you ask one of the hardest questions. If we have multiple, totally independent noise source, to tell the truth, this is still largely unsolved problem. Yeah, it's hard to you hear two noises, totally independent, the random ones, from two sources. That's still, largely unsolved. Next week we discuss subspace method that's actually targeting the kind of Kalman filter type of system modeling. You need to model both process noise and measurement noise, but it's very difficult to separately identify these two noise characteristics. Yeah.
I see. Thank you.
Okay, John, you ask. Lambda can be a matrix because of the same reasons. We stay with the scalar case. Yeah. And Charles again, we
were just discussing this question.
Oh, is that right? Okay. One point is just wondering if there's a way to show that without doing it. Okay. And John again, good point. Probably. So. So, back to this. So that is about the. Hey, John and Charles, which slides are you talking about? Which part are you talking about?
No, we were just discussing whether you could generalize to multivariate noise.
Oh, yeah. That's hard. Yeah. Okay. Yeah, and Jacob. Oh, didn't find. Maybe Nick hasn't posted that data yet. I guess. Yeah, sorry about that. I will actually ask him to do it quickly. Yeah. Okay. Now, we have a little bit more time. I have some other very practically important materials to share with you. So I hope we have more time. Okay, so the one important issues in applying the system identification things is input design, right? So you have some systems in front of you, and then you really want to actually get the best mathematical representation of the systems, right? So system identification, we basically implies often cases we quietly assume that the input can be selected. We can design the input, and then that the designed, very cleverly designed input that can be provided to the systems and see the response to it, right? So given, having said that, the question is, so what is actually the signals you should provide to the system? So how you design the inputs, right? So looking at some practical issues, previous analysis all said that, bigger input is better because the signal to noise ratio, bigger input is good. But actually it has some physical limit, and the sensor also has a physical limit. So, you have to stay within actually some upper and then lower limit for the input, right? So, yeah, how we can actually satisfy such physical limit and then create the input signals. So let's look at the two cases. So one is that somehow going up and down, this kind of signals are given to your systems, but at this time it has some high peak, and most of the other times a little low. Okay, the other signals is almost the same magnitude, no particular high peak, involved here. So we must be careful, this kind of stuff, it's good in meeting the physical limitations, but it must have some, requirements. Signals must be rich enough to excite the whole, systems, right? So we must have a good signals, right? And then uncorrelated, mostly white signals is the best. So now actually, for us to tailor the input to signal shape, we have one matrix being used. It's called crest factor. And then CR, crest factor, is given by maximum of U square. So in this case, this is the highest value, right? So signals maximum U square, over the time of 1 to capital N, divided by square norm of that signals. Basically U square, some an average variance. Okay, and we assume that this U is actually mean zero, and this guy is basically mean squared, right? So this actually variance. If this value is large, we don't have actually big peak, but signals is mostly very large, right? On the other hand, if this one very small, if the CR is very large, that's actually very bad. Just occasionally you have a very high peak like this. And most of the cases, the signal is very small. That makes this one is large. But small CR square means that the maximum and actually the average value of the strings almost the same. So the best case is CR equal 1, smaller is better. So what kind of signals makes this one the best in this sense, CR equal 1? What sort of signals make this one to be 1? That turns out to be, anyone?
A constant signal?
Oh, yeah, some constant, right.
Sine wave or something?
Yeah, it is binary. So it hits the maximum peak and then hit back to minimum negative side of peak. But a signal must be rich enough, right? So just on most signals, how can you make that very rich? Rich in the sense that spectrum is just a spread, all frequency. And then autocorrelation, on the other hand, is just, lambda, only when t and the tau equals 0. T and S are the same. How can you create that signals? Well, this on-off signals, but if you vary this basically, interval randomly, interval to be changed randomly. Yes, in theory, you can create so that it's, autocorrelation is to be just, lambda when tau equals 0 alone, and the other is just a flat 0. For that, if you take the power spectrum, it is just flat the lambda throughout minus pi to pi. Remember that? Right. So this is one of the best signals because crest factor is 1, right? And you get the very large signals pumped into the systems, and the system is actually sufficiently excited, and with this actually conditions, that's actually white signals, uncorrelated signals. And this random binary signals, of course, to some extent, this is an approximation. So I put the pseudo random binary signals can be created quite easily. Well, these days, it's being made in some special chips and something existing, but it's being produced with a very simple logic, and that's basically just you use some shift register. And the shift register, right? The 0, 1, 0, 1, this is something input comes in, and that one is actually stored here. And then previous one shifted here, the previous one is shifted here, shifted here, shifted here. Now, if you create some kind of feedback, if this one 1, 1, and then 0 is to be an out, that kind of logic is created, you can create the some, 0, 1, 0, 1, signal stream like this. And if you design this feedback loop, feedback logic in a proper way, you get the pretty long non-repeated pattern. So in this case, it's just a 5 bits actually shift register with the proper feedback logic. It is to create a 31 bits of unrepeated 0, 1 signals. Of course, after 31 time slots, the same pattern is repeated. But I know this is the case when you have only 5 digits, right? If you double this in 10 digit or more, you get to almost infinitely long sequence, no repetitions happening, and that actually create the white signals. So this kind of pseudo random binary signals are being used quite extensively in the system identifications. The another thing is actually it's natural to think about some sine waves, right? So a multi-sine wave, if you put together multiple frequency components like this, in this case, frequency omega 1 to omega p is to be superimposed with the phase angle phi k and then amplitude ak, right? Let's compute the crest factor of this, amplitude of ut in maximum value divided by square root of signal power. And if you compute this, it is basically a case, in the case. We look at the amplitude is worst case when they are all in phase, you get the high peak like this. So, worst case, if you have all same parameter values, this crest factor becomes square root of 2p. So p is the number of sine waves with the different frequency components. So as you superimpose many frequency into this, you get the very bad crest factor, right? So, when you use sine waves, usually one at a time, p equal 1, that's the square root of 2. It's somewhat close to 1, so that's good. And so one at a time. How you and whereas you really need to sweep out the frequency from low frequency to high frequency, right? Relatively short time, and maybe that is a requirement. So if that's the case, it's actually appropriate to use this signal. It's called the chirp signal. Chirp signal. So frequency is moving up from some low level to high level, constantly like this. Then your actually signals is this kind of a cosine or sine functions with the varying frequency. And so this is one example, low beat to high beat. So if I put the speakers in here and then create some sounds associated with this one, it sounds like boo. Do you get it? that is actually chirp signals. So that's the way people use. And this chirp signals is so popular. So if you read some articles, the experiments were conducted such and such with the chirp signals from this frequency to that frequency, and then actually, it has a certain actually a covariance expectation. That's actually the right experimental data you take. So surely you see that kind of stuff in some of the literature. Of course, chirp signals have certain weakness, and so you need to use that carefully. And there are lots of improvement being made. For instance, Professor Garrick McKinley, he developed a very important improvement to chirp signal. So if you have a chance to talk to him, that's his favorite work. So there are many things happening. Okay, that's all about it. I need to say today. Are there any questions or concerns or something to clarify? Just a quick reflection. So, our goal is to do some kind of theoretical analysis, as you collect more data. Where are we really going? And then it's going to central limit theorem. So nice, Gaussian distributions. The key point is, how quickly it is to converge, and then the variance depends on signal strength, input signal strength, right? And actually sensitivity. It's a very important point. So when you don't actually include some parameters which are insignificant, that's not playing an important role, and also difficult to estimate, difficult to identify. So that's actually needing a little bit more careful treatment as to what the sort of model you should put together. Okay, so that's all about it. Yeah. Okay, have a good one. Yep. Take care. Bye.
Thank you.
Bye.